So starting with our today's session, semiconductor era is proving itself as the best for the upcoming future of this century. Good morning, everyone, honorable delegates, dignitaries, and our respected speakers and all dear participants. I feel privileged to extend my warm welcome to you all. I first want to congratulate you all for the success of this journey that we are on. It has been possible only because of you all, our honorable speakers and dear participants. I welcome you all for the day 4 of this short-term course. For today's session, we are indebted by our respected speakers, Professor Sajad Ah Lone and Professor R.K. Sharma. We wish you, our participants, a very happy and knowledgeable journey throughout the session. Now, I would like to request Khushbu to introduce our first speaker for today's session. Khushbu?
Good morning. Good morning, everyone. I, Khushbu Iqbal, feel privileged to extend my warm welcome to you all. Starting with our 7th session for day 4, I would like to introduce our speaker, Professor Sajad Ah Lone. Professor Sajad Ah Lone currently working as a professor in Jamia Millia Islamic Central University, New Delhi. Professor Sajad Ahmad received BE in Electronics and Communication Engineering from National Institute of Technology, Srinagar, Kashmir, and the PhD from India Institute of Technology, IIT Kanpur. He has authored and co-authored more than 100 publications in reputed journals and conferences, received 6 Best Papers Award in various international conferences around the globe, and has filed 9 patents. He has completed many national and international projects, including one multi-million NPST project from Saudi Arabia. Dr. Sajad is a visiting professor to the King Saudi University, as he has been awarded the prestigious VPP Fellowship by the King Saudi University in 2015. He has been awarded Indo-Canadian Shastriya Fellowship by the Government of Canada and India, and as a Shastriya Fellow. I would request to Professor Sajad sir to kindly start with his session. Please, Professor Sajad sir.
Very good, Khushbu Iqbal. Very good. Khushbu. Khushbu? Khushbu. Sajad sir, Assalamu alaikum.
Walaikum salam.
ठीक है चल.
Everybody.
Now you can share your screen.
Yes, share your slide. Share your slide. Khushbu. Oh, yes.
Yes, sir.
Very good. Thank you. Very good.
Yes.
Very good.
Okay, may I start now?
Yes, sir. Please.
Yes.
full
Yes.
screen.
Yes.
Am I visible? Am I audible?
Yes, sir. Yes, you are
Is my presentation visible?
Yes.
audible.
Okay. Okay, thanks a lot. So, first of all, I would like to thank the organizers of this workshop for inviting me to deliver a talk. So, I'll be talking about multifunctional nanoelectronic devices, which have been developed to enhance the Moore's law. First of all, by device, I mean transistor. Device level of abstraction actually means transistors in electronics world. So here I'll be talking about some devices which are multifunctional in nature. Multifunctional means a conventional transistor is just working as a transistor. And we combine transistor to realize a circuit. Right? We combine transistors to realize a circuit, then to realize a gate, and finally we can realize an integrated circuit. But a basic building block is a transistor with single function, to be just a transistor. But we do have a lot of problems which I'm going to discuss. By multifunctional means designing, realizing a transistor which will not act as a transistor but directly realize high level of abstraction. Means with a transistor we can directly realize an inverter action. With a transistor, single transistor, we can directly realize a gate action. And with a transistor, single transistor, or just a couple of transistors, we can realize an entire Boolean equation. I do hope in the audience, I have people who are well versed with digital electronics, digital designing, at least gates, semiconductor device gates, flip-flops, right, memories. So I'll be discussing transistors, which can directly realize this high level of abstraction. Okay, so when we realize a Boolean equation, which conventionally needs dozens of gates, and when we say dozens of gates, it means it needs hundreds of transistors. So if we realize a Boolean equation by a single or by a couple of transistors, it means the system is going to be highly compact. So if we have a highly compact system, it means we have kept Moore's law alive. I'll be talking about Moore's laws. Okay.
Zahid Wali.
It's not moving. Slide is not moving. Is there any? Do you have any? Do you have control with you?
Okay.
Naklesh,
I'm unable to move the slide.
Sir, please
Naklesh,
click on the
Naklesh.
slides
Yes.
or use the arrow keys.
Yeah, I'm using arrow keys, but
Sir,
it's
can
not
you
moving.
please right click then?
No. It is not moving at all.
So you must stop share and then start again sharing.
Wasifam.
Yeah. Okay. So
Very one.
this is the outline. I'll be talking about first design objectives. Then I'll be talking about how we achieve these design objectives by scaling. I'll be talking about the state-of-the-art devices. What are actually the problems with these state-of-the-art devices? Or we can say, what is the problem at a device level of abstraction? And then I'll be talking about why we need multifunctional devices. And finally, I'll be talking about some
Hello.
word. So the second objective is that the power consumption, energy consumption of the devices should be as small as possible, right? So small energy consumption will give me large battery life, because most of the devices, almost all the portable devices are battery operated, and it is always, we always wish that the battery life should be as high as possible. We should not frequently, there should be no need to frequently charge our battery in a portable device. For example, our mobile, our laptop, or small gadgets. With small power consumption, we actually address a very important issue in electronic devices, that is the thermal self-heating.
Internet.
The magnitude of the thermal issues, I mean, in the devices, the device should be as cool as possible, and this is possible only if we have, I mean, if the device has no thermal. speed of the system. Third objective is that the speed of the system should be as high as possible. So whether you design a device or you design a circuit or you design an integrated circuit, the speed of the system should be as high. So this is the third objective in electronic design. The fourth important objective is the functionality. The number of functions to be performed by a device to a processor should be as high as possible. If you recall, the first microprocessor in early 17 was having a limited functionality. But now we have the state-of-the-art processors. State-of-the-art processors have large number of functionality. We have a full-fledged computer in our mobile, in our handheld device. So this is an important objective, that the functionality should be as high as possible. Then we have an important objective is the cost, or cost per bit. So whatever you are going to design, the cost of that should decrease, right? So we must design objectives, we must design processors, ICs with a lot of functionality, but at an important point is that the cost of that device should be as small as possible. If we have a significant increase in the cost, then we may not go for increasing the functionality of the device. Then we have one more important objective, noise margin, or the impact of the noise. So whatever you are going to design, the impact of the noise should be as high as possible. Impact of the undesired, unwanted signals should be as small as possible. Our device, our system should be reliable. It should be robust. The effect of temperature, pressure variations, humidity, radiations should be as small as possible. And finally, whatever we are going to design must be long-lasting. So these are the design objectives which each and every designer has in mind while designing a device, while designing a circuit, while designing a gate, while designing a block, while designing a full-fledged system. So whether the designer is from electronics domain or electrical domain, mechanical domain, or any engineering domain, these are the objectives. So keeping these objectives in mind, electronic device designers, they try to design devices which have all these objectives. Means speed should be high, power should be as small as possible, packing density large, functionality large, cost small, noise margin as high as possible. It should be reliable and long life. And we try to achieve these objectives at different level of abstraction. The lowest level of abstraction at which most of you people work, I mean the nanoscience people, is a material level of abstraction. So people working at the material level of abstraction, their objective is always to design and develop materials which can ultimately give me high speed, which can ultimately give me reduced power consumption, which can ultimately give designers large packing density ICs, which can give me functionality very high. Of course, the cost should be as small as possible. Impact of the noise should be as small as possible. And the system should be highly reliable. So all these things can be achieved as various abstraction levels, the lowest one being the material level of abstraction. So material people, material scientists, they always try to design a material which is efficient in all these parameters. But once the material scientists, material engineers have given us the material, the job of a device designer starts. The device designer, the electronic designer, actually takes that material and tries to realize a device. It is, for example, we have a material, it is silicon. It is there from last around 5-6 decades, and it has served us a lot. Silicon has a lot of advantages. But now we try to extract more and more performance of the silicon. So it is not possible. That is why material engineers, material scientists, they try to develop new and novel materials, right? Similarly, silicon was there, and with the silicon there was germanium. So earlier the focus was on silicon because of the lot of advantages, and the germanium was forgotten. But now since we try to extract more and more performance out of the devices, out of the silicon, but it's not possible. Now we are taking the help of other materials, for example, germanium. So we have silicon germanium material, silicon germanium technology. So we have actually combined the silicon and germanium. So we have a new material system. This new material system gives me high speed than this conventional silicon-based system. The reason is that the germanium has large mobility than the silicon. So if we take this germanium and combine it with the silicon, we have a device which gives me mobility around 3 times more than that of silicon, right? So in, for example, a MOSFET, we had the channel through which charge carriers move. So in the conventional silicon device, the channel was made up of silicon only with limited mobility, right? Less than 1500 centimeters square per volt second. But if we replace this channel part of the silicon MOSFET with germanium, germanium has mobility more than 3000 centimeters square per volt second. So we can easily get a speed enhancement by 3 times, because speed is directly related to the mobility. Drain current is directly related to mobility. So in the germanium devices, we have large mobility and we can extract more and more speed, right? So this is what people who work at a device level of abstraction. So people work at a device level of abstraction, they take the material and they try to realize all the parameters which I have mentioned above. Then after combining the devices, we can have a gate. We have AND gate, NAND gate, NOR gate. So these are the gates. And if you see in a gate, we have the transistors. So if you have selected a best material, if you have designed a best device, you can get a best gate. So best gate means high speed gate, low power consumption gate, and all other parameters. So if you have efficient gate, you can have an efficient block. If you have an efficient block, you can have an efficient system. For example, a processor. So it all depends on the abstraction level. So we have different people working at different abstraction level, and their objective is same. 1 to 8, these objectives, they remain same whether the person worked at a material level, at a device level, at a gate level, at block, system, architecture, and algorithmic level of abstraction, right? So now till date, we try to achieve these devices, achieve these objectives by scaling the dimensions of the device. So it was scaling, it was reducing the dimensions of the device, which have actually helped us to achieve these objectives. But the problem is that, is it possible that we can continuously scale the dimensions of the device? If no, what are the hurdles? And if no, then what is the alternative? If we cannot make the device, technology node scalable, if we cannot scale it further and further, since of course we cannot have technology node of 0 nanometer, we cannot have 0 nanometer technology node in a device. Okay, so we have a finite, but with a finite technology node, we do get finite performance. But the need of the era is that the performance should be as high as possible. So this scaling, we have a limitation in scaling. We have a hurdle. We cannot scale it further and further and further. So if we are unable to scale it, then what is the alternative? So that alternative, I'm going to discuss over here. Okay, so first, these are the objectives. These are the advantages of scaling, which we have, followed till date. By scaling, the space, the area has decreased significantly. For example, in early 40s or 50s, there used to be vacuum tube era. The space requirement was very large. Now we have MOS technology, we have emerging electronic device technology. The space requirement has got, significantly reduced. So by scaling, it is all because of the scaling of the device dimension. So second, if you see here, the scaling has reduced the delay. The scaling has actually increased the speed. If you remember the first processor, the first microprocessor in early 70s, the clock frequency was in kilohertz. The clock frequency was in kilohertz, and now we have the state-of-the-art processor with a technology node of, for example, 14 nanometers. The clock frequency is around 4 gigahertz. So we have got shifted from kilohertz to gigahertz. This transition from kilohertz to gigahertz is only because of the device dimension, because of the scaling of the device dimension. So because of this scaling, the clock frequency, the speed has got enhanced by 1 million times, because if you move from kilohertz to gigahertz, it means it's around 1 million times, 10 is for 6 times. So all because of scaling. Now again, if you see the energy consumption has drastically decreased in the vacuum tube technology to semiconductor devices. Again, this is attributed to the scaling, because when you scale the dimensions of the device, smaller devices always consume small energy because of various reasons. And of course, the cost. This is a big thing. This is a big thing in semiconductor devices. The cost has got significantly reduced. Okay. So all because of the scaling of the device dimensions. But again, the problem is that we cannot continue with this scaling. This slide you must have seen multiple of times. Actually, Richard Feynman's, we can say, behind this scaling or behind this significant increase in transistor count in clock frequency is his statement. He has made a statement long before. And the statement is that why we cannot write the entire volumes of encyclopedia on the head of a pin. So it means head of the pin, if you see the area of the head of the pin, it is very small. But he challenged at that moment to the device designers that try to realize the entire encyclopedia on a head of the pin. And then he made a famous statement, there's a plenty of room at the bottom. All right. This is what, the people in nanotechnology or device designers repeat this statement often. Now, if you see here, that was a dream. And today we have the realization. This statement is old. Today, a NAND flash of 4 GB can hold approximately 100 to 200,000 pages of text. Okay. Today, we are in a position to make dozens of encyclopedia to get stored in a very small area. And again, this is all because of the dimension, because of the scaling of the device dimensions. And that was a dream. And Gordon Moore is a person who tried to realize the dream, who tried to develop ICs, integrated circuits, with large number of transistor count. So Gordon Moore was a founding director of well-known Intel organization. So if you see, we have the processors, most of the processors from Intel. The founding director of that was Gordon Moore. And this Gordon Moore has actually provides as a push to device designers. He has made 3 statements. And if we are able to keep these 3 statements valid, we can say Moore's law is valid. His first statement is that the transistor count in memories should double in 18 months. And the transistor count, second statement is the transistor count in processors should double in 24 months. So 2 things, he made 2 statements actually. He said that the people in designing, people in fabrication, device designers, they must put in efforts. Technology must grow in a way so that we can, in 18 months, double the transistor count in memories. On the other hand, he has given us 6 extra months in case of processors. He said in processors, the transistor count should, double in 24 months. The reason is that in one case it is 18 months, shorter time. The reason is that memories are regular structures, the design is not complex. That's why he mentioned that the designers must double it in 18 months. On the other hand, people who are designing the processors, he has given them 6 extra months. He said that in 24 months, you must double the transistor count in a processor. It means today, if the state-of-the-art processor has 1 billion transistor, okay, scale the technology node in such a way so that after 24 months, the future processor must be having 2 billion transistors. So if we are able to realize, if we are able to double transistor count in 24 months in case of processors, we can say Moore's law is valid. Similarly for memories, if we are able to double in 18 months, we can say Moore's law is valid. But he made a third important thing. Word of caution is we can double, or you can double the transistor count in 18 months, in 24 months. But remember, the cost of the foundry. Foundry is a place, foundry is a system, it's a setup where we actually fabricate a device. He said that the average cost of the fab lab, foundries, double in every 2 to 3 years. So if we try to develop, if we try to have a foundry today, and if we invest $1 billion in a foundry, we have to update this foundry in 2 to 3 years again. And at that time, we have to invest around this much amount of time, money. Why is it so? The reason is that since the technology node changes, our objective is to achieve more and more performance. We try to achieve it by scaling. So when we try to achieve it by scaling, we reduce the technology node. And when we reduce the technology node, the foundry is no more valid to realize that device. Okay. So if you have a foundry which fabricates 1 micron technology node device, that foundry cannot be used to realize 14 nanometer technology node. So we have to, replace, we have to update the entire system. Similarly, foundry which can realize silicon-based circuit, that foundry cannot. Okay, so if you change the setup, so this is the reason cost of the fab labs.
Hello.
Unfortunately, we don't
Sajad
have
sir.
any state.
Hello, Sajad sir.
That foundry processor.
Hello, Professor Sajad.
We haven't updated. After but we are nowhere.
Hello, Professor Sajad. Hello. Sir, excuse me.
Yeah, I can hear you.
Sir, actually your internet
I
connection
can
is
hear you.
weak. I think that's why your voice is breaking a lot. We cannot hear you properly.
See, I cannot address that problem. I'm sorry, you had to bear with me.
Sir, if you can try turning off your video, then might be possible bandwidth might increase.
Yes, yeah, I can do it. I can do it. Okay.
Okay.
Okay, am I audible now?
Yes, yes, sir. Yes, sir.
Is it better now?
Yes, sir. It is better.
Okay. Okay. You should have told me earlier. Uh, okay. So let me again repeat this slide about.
Sir, it happened only
What Moore has.
1 minute ago.
Okay,
You only
1 minute
started.
ago. Fine.
Yeah. So whole
Briefing.
presentation is
Okay.
okay.
Okay, fine. So Moore has actually given us 3 statements, and we device designers are supposed to follow these statements. Then and only then we can say that Moore's law is valid. His first statement is that the device designer should double the transistor count in 18 months in case of memory. And the device designer should double the transistor count in 24 months in case of processors. So 18 and 24 months, 18 and 24, 2 numbers he has assigned. One for memory and another for processors. For the memory, he has given us a shorter time. The reason is that memory is a regular structure. Okay. On the other hand, processors are complex. And with the state-of-the-art processors, the functionality is increasing day by day. So increasing functionality means the complexity of the processor actually increases. So this is the reason that Moore has actually mentioned 24 months for processor, for microprocessor, for transistor doubling in microprocessor. And in case of memories generally have single function, that is storage. So memories have single function storage. That's why Moore has mentioned that try to double the transistor count in 18 months in case of memories. But at the same time, he has mentioned a word of caution is that when you double the transistor count, you will face the issue in terms of fab lab complexity and cost. Since when you scale the dimension change, you have to update the foundry, increase the fab cost. So this is mentioned that the cost of the is bound to 3 years. And this is the reason that in India, we don't have any state-of-the-art foundry which can fabricate a device with the state-of-the-art technology node. We have one foundry in Mohali, but that's not updated one that can just fabricate some power devices with technology node in microns. But now the technology node has reached around 10 nanometers. We do have working devices with 10 nanometers technology node. So we cannot use that foundry for the fabrication of the state-of-the-art devices. Okay, so this is what he has mentioned. And this is what people are trying to keep alive. So device designers, they put in to double the transistor count in 18 months in memory, transistor count in 24 months in processors. And till date, they have been doing this by scaling on, by reducing their dimensions. But now, if you see here, if we see the state-of-the-art processor, the Ryzen-based EPIC processor, it has 19.2 billion transistors. So this data is of 2017. It was realized around 3-4 years back. So the technology node is 40 nanometers, and the transistor count in that chip is 19.2 billion in 2017. And now, if we see the state-of-the-art processors, since the technology node has actually got scaled down below 40 years, we do have processors, we do have memory with transistor count more than this 19.2 billion transistors, all because of the scale. Okay. Now I'll be talking about some, the conventional technologies where we actually started. The device designers started with the bulk transistor, bulk MOSFET, the conventional MOSFET. Conventional silicon-based MOSFET. The silicon-based MOSFET or the bulk technology has a lot of advantages. It is because of those advantages that we still have the bulk technology. The advantages are the technology is mature. It is low cost because of a lot of efforts. Foundries are around the globe are there, and at the device level of abstraction, we have some. Breakdown strength is large. The important is the bulk device is thermally efficient. So, in spite of all these advantages, we do have a lot of. We cannot continue with the bulk technology now. The reason is that bulk technologies face severe short channel effects. Short channel means when we reduce the dimensions, when we scale the dimensions of the channel. So at a point we say the device comes in short channel domain, right? So whenever we have a short channel in the device, the big problem is in the form of control. Control is lost. In a MOSFET, the control of the channel should be with gate only. So in a scale device, in a short channel device, the control is no more with the gate. We have a drain, we have some other parameters which influence the device, which influence, for example, the drain current. So whenever we have other influences, whenever we have influence other than that of the gate, we can say the device is not a controlled device. We have reliability issues, we have leakage, we have increase in static power consumption. These are the problems with the bulk technology. That is why we try to stop using bulk technology. Now, we have some better alternatives. The better alternatives is in the form of silicon on insulator structures. So we have structures, for example, this is bulk. This is just semiconductor substrate. In the semiconductor substrate, if we create a buried oxide box, silicon dioxide, for example. So the structure is being called as SOI, silicon on insulator structure. We have two types. We have fully depleted, partially depleted. I will not give the details. So this type of structure, we call it a SOI structure. And the SOI structure has, addressed most of the problems in the bulk. We have the problem is parasitic capacitance is large. It gives me large speed, large packing density. And one of the biggest problem over here is latch-up problem. So that latch-up problem gets addressed. But the biggest advantage of the SOI is, particularly in case of the thin film. Thin film has the best SC suppression. Short channel effect suppression in case of SOI is the best. But again, we're not getting things free of cost. We have the problems. Problems with this type of structure or this type of technologies, it is thermally inefficient because of this oxide. So whatever heat gets generated over here, it is difficult for that heat to get dissipated because this is preventing. This is an insulator. So this is the big problem. Thermally inefficient. We have poor breakdown strength. Initial and fabrication cost is more because we have to create, a wafer which must be having this box. On the other hand, we don't need any kind of box. So initial fabrication cost is more. And since it is impossible to have very thin film. So when we don't have thin film, it means again we have short channel effects, SC suppression, right? So this is what SC means, short channel effects. See, when we scale the dimensions of the device, when we make this L, channel length of a device, smaller and smaller and smaller, see, this is what happens. The threshold voltage actually decreases. So VT decreases with L, of course, when we have high VDS. So just remember, whenever we decrease L, the threshold voltage of the device decreases. We call that VTH true log. So whenever we have a decrease in threshold voltage with a decrease in L, we face SCEs, short channel effects. And whenever we have this type of behavior, VTH decreasing drastically, the control gets lost. So device is no more a controlled device. We have uncontrolled behavior. We have large leakage. We have large self-heating effects. So the SCs are because of charge sharing, because of subsurface punch-through, because of drain-induced barrel loading. These are the factors which are responsible for all these things, right? So when we try to realize novel device, our objective is always that this charge sharing, the subsurface punch-through, this DIBL, these three things should be prevented. So if we are able to prevent these things, we can scale the dimensions of the device further and further. And in that case, we can have threshold like this. So if we control these things, these three factors, charge sharing, punch through, and DIBL, we can have, threshold voltage invariant L. So we go on increasing L and decreasing L. If you see here up to this point, the threshold voltage more or less remains same. So we can efficiently scale the device, right? So this is what we try to achieve, try to do in nanoscale devices to have this SCE suppressed. Okay, so this is again, thin film SOI structure. These are the advantages, but I mentioned these are the problems, right? So if we address these problems, thermal inefficiency and heating, we can have the best possible solution for SCE suppression. A few years back, we have proposed a structure. We have proposed a structure which is again based on the conventional MOSFET technology. But in that device, we have used SOI, but a broken SOI with a window in the SOI over here. And we have used some highly doped regions. The highly doped regions are being called as partial ground planes. So the use of these partial ground planes and this broken window has given us many advantages. This broken window has given us a path for the heat which gets produced over here to get dissipated. These ground planes, they actually reduce the interaction of this region and this region, drain and source. So when we reduce the interaction and when we increase the dissipation, so it means we address two important issues. One is that SCs get suppressed, and the second is thermal issues have got addressed. So if you see this structure, the green one, in the green one, we can easily go on scaling the device dimensions. Because if you see the roll-up over here, roll-up is much better than the roll-up in this black and the red curves. These are the conventional structures. So the problem has been to some extent realized by having a PGP structure, but again, the structure is complex. And we try to address these problems by using metal source drain SOI devices. So instead of using the conventional doped structures, conventional doped source, conventional doped drain, we have used metallic source and drain. So when we use metallic source and drain, a lot of problems has got addressed, and we got a lot of advantages. When we use metal, you all know that using a metal in the source, using a metal in the drain, an important issue is the source drain resistance. That source drain resistance has got decreased significantly. So when we have a reduced source drain resistance, we have improved performance. In addition that, we have eliminated the latcher problem in the conventional structure. So this is what metal source drain SOI structures has given us. But again, the problem is that complex fabrication process. This is not, things are not easy. Again, if we go for the metal drain, metal source drain structures, we have the problem in terms of the drain current. The drain current decreases. So we do have problem with this type of system also. So these are the advantages. Metal source drain device have planar structure. So it is a simple structure. Metal source drain structure gives us the abrupt junction. Metal source drain structures, we don't have latcher problems. If we compare fabrication of metal source drain structure with the conventional doped source drain structures, the process is low temperature. So it is easy to fabricate a metal source drain structure than the conventional from the temperature point of view. But again, the problem with this concept is that we get low on current and hence low ion-IF ratio. These are two important performance measuring parameters. We always wish that the device should give me large on current and the ion-IF ratio should be as high as possible. So keeping in mind the improvement of the various performance measuring parameters, different structures have been proposed by designers. You must have heard about FinFET structures, SY FinFET structures, SY tri-gate structures, pi-gate structures, gate-around structures, nanowire structures. So all these structures have been designed and developed. What is the ultimate objective? The ultimate objective is to control the channel. We should have more and more control on the channel. So when we have more and more control on the channel, the short channel effects get suppressed. So we can scale it further and further. And when we are able to scale it efficiently further and further, we can keep most the valid and alive. So all these structures have been designed till date with this objective, that SC should be suppressed, that the Moore's law should be kept valid in future also. So briefly, since we have many people working in, at a material level of abstraction, so conventionally, if you try to realize various domains, various region in a device, for example, you try to realize emitter, base, collector, source, channel, drain, we always try to realize them by doping, by diffusion, and by ion implantation. But with the diffusion and ion implantation at the nanoscale, when we have a nanoscale device, we have a lot of issues. The biggest issue is that since nanoscale device always demands that the junction should be sharp, PN junction, it should be sharp junction. But at a nanoscale, by conventional doping and ion implantation, it is difficult to realize that sharp junction. Second important issue is that series source drain resistance. So when you make a nanoscale device, the source area, the drain area, the channel area is, the thickness is very small. With the result, we have a significant increase in source and drain resistance. Again, a big problem. Third big problem at the nanoscale is the dopant concentration. Actually, we need dopant concentration above its solid solubility limit. This is the big problem. We need dopant concentration more than that of solid solubility limit of the device to address the problem of series and drain resistance. Again, a big problem. The accurate control of doping, N-type, P-type, the accurate control is difficult at nanoscale. And at nanoscale, we have random doping fluctuations. The doping fluctuations, because of the doping fluctuation, we have, for example, the change in the threshold voltage of the device. So whenever we have doping fluctuations, whenever we have VTH fluctuations, we have an uncontrolled device. And realizing pure N-type impurities in emerging material. For example, gain. In case of gain-based devices have a lot of advantages. But in a gain, to realize P-type gain is extremely difficult because activation energy requirement is large. And similarly, in case of CNT, for example, the chemical doping is not straightforward. So we do have a lot of issues associated with doping at a nanoscale. So how to address this problem? We can address this problem by altogether replacing the doped structures. Altogether realizing that doping, conventional doping, not by the conventional ways, but by a technique which is being called as charged plasma device. Charged plasma. In the charged plasma structures, what we actually do, we create source region, we create drain region, we create emitter, base, and collector in devices, not by doping or diffusion. So there is no concept of diffusing impurities or ion implantation. So we can just realize these regions by laying a metal over the surface of the semiconductor. So when we lay a metal with a particular work function over the surface of the semiconductor, it gives me N-type, it gives me P-type, it gives me N-positive, it gives me P-positive type of regions. So we need not to go for actual doping and ion implantation. Just lay a metal with a particular work function. With a particular work function, we can create, doped regions, right? So in the charged plasma devices, we don't have doped source, doped drain, nothing like that. Just metal at the top of the surface. It gives me N-type, metal with a different work function. At the top of the surface, it gives me P-type. Similarly, if you need, wherever and whenever you need a doped region, don't dope. Just have a metal, just design, just select a metal with particular work function. Of course, it must follow some, conditions. These are the conditions for, work function, electron affinity, band gap. See here, this is for charge plasma, this is for, electron charge plasma, this is the criteria, and this is the whole charge plasma, this is the criteria. So if we satisfy this criteria, we can create whole charge plasma without actually doping. If we satisfy this condition, we can actually realize electron charge plasma without, doping and ion implantation. So these are some structures. I will just show you the structures. These are the charge plasma structures where we haven't used the concept of doping. This is the charge plasma based Schottky metal based MOSFET. No doping. This is here metallic source, metallic drain, and over here we created, this source extension has created a charge plasma in this undoped silicon. So this type of structure has given us a lot of advantage, lot of improvement in the performance. For example, the drain current has got significantly increased. If you see here, this is the charge plasma blue. Similarly, if you see the cutoff frequency, the red one is the charge plasma of this one, and this is the conventional, significant increase. Similarly, we have designed electrostatic dope segregation layer. Again, a Schottky barrier MOSFET, where we have used the concept of charge plasma over here. Just metal, it will induce charge plasma in this undoped silicon. So we get a significant increase in performance. This is, recently developed a biosensor. In this biosensor, we have used the concept of charge plasma to sense biomolecules. These are the biomolecules, and these biomolecules can get trapped over here. Okay, so we have the biomolecules over here with the result dielectric constant change over here. Then we have the charge plasma, the plasma which gets induced by the metal, that gets changed by the biomolecules. So accordingly, we can say that we have actually created a biosensor has created which can sense these molecules. Okay, then we have the state-of-the-art transistor, which is being called as a tunnel field effect transistor. The tunnel field is there from last, it's a novel structure. From around 1 decade, we have this tunnel field, people working on this, people working in this domain. Again, tunnel field objective is same, because the conventional MOSFET has issues, and we try to address those issues by having tunneling in a device. So this is conventional one. In the conventional structure, we have thermionic emission. Thermionic emission means the charge carriers, they need to cross a barrier over here. This is the conventional structure, conventional MOSFET. But in case of TFET, we have redesigned the structure, the device in such a way so that we don't have the thermionic emission, we have band-to-band tunneling. So this band-to-band tunneling has given us a different type of structure, which is being called as a tunnel. So if you see the characteristics, this green one is the characteristics. This is the transfer characteristics for different structures. So if you see, this green one is the characteristics for TFET. So this is the advantage. The subthreshold slope. We get the optimum, we get the best possible subthreshold slope in case of TFETs, right? With the conventional technology, remember the conventional technology has a limitation. The subthreshold swing is limited to 60 millivolt per decade around. Okay, this limitation has been overcome in case of TFET. In the TFET, we have subthreshold less than the 60 millivolt per decade. And a fabricated TFET, recently TFET has been fabricated with this subthreshold slope around 20 millivolt per decade, right? So when we have a reduced subthreshold slope, it means the off-state conduction. This is the off-state conduction, the intercept on the drain current. So in this case, the lines, this line remains parallel with this one. So it can have intercept at infinity if it goes parallelly, straight downwards. So we can say here, the off-state in case of, in TFET structures, we have the highly reduced off-state conduction. But again, we have some problem. The problem is, this is the problem. If you see at this point, this is actually the on current. The on current in case of TFET is less in comparison to the state of the art. That is why people are trying, to put in efforts to push this green in the upward direction. So if we are able to get this green equivalent to this one, right? I mean, the conventional MOSFET, we can have the best performance out of the TFET structures. And then we can see the state-of-the-art processors made up from TFETs only. Right? See, we have different structures here. Silicon germanium is there, third, fifth compound-based semiconductors there. So we do have large on current here. But again, if you see the off current in these structures is very large. So ion ratio is poor. And at the same time, if you see the subthreshold slope of these curves is again inferior in comparison to TFET. Right? So TFET has this problem of on current in comparison to this one, but TFET is outshining all the conventional structures in case of on current, in case of off current, in case of subthresholds. So with the TFET, it is possible to scale the dimensions further and further. So these are some other TFET structures where we try to improve the on current performance. We have inverted C tunnel junction FET. Again, we try to improve the on current. We have vertical gate elevated source TFET. Oh, again, the objective is to increase the on current. We have quadruple gate TFET. This structure has given us a significant increase in the TFET, right? So if we are able to fabricate this device, this can definitely outshine the conventional technology. We can have dual MOSFET, MOSCAP line TFET again. Okay, so these are all devices. These are all transistors. Again, see, a lot of efforts have been put to improve the performance of these transistors, to make them smaller and smaller and smaller, so that we can have a smaller circuit, so that we can have a smaller gate, smaller block, and smaller system. But again, we do have a lot of problems with the device level. Now, this is the need of the hour. The need of the hour is multifunctional devices. It means directly design a transistor which will work as a gate. Directly design a transistor which will work as a block. Directly realize a transistor which is going to realize entire Boolean equation. So this is what the concept of multifunctional devices is there. So we have developed a structure which we call as triple S device. This device is a single transistor based inverter. See, if you see here, this is the conventional structure, conventional inverter. We use NMOS and PMOS transistors, two transistors. So two transistors realizing an inverter. On the other hand, we proposed a structure. We proposed a structure which is single device. This is a single device structure, and the single device structure is directly realizing an inverter. So this can realize NMOS, this can realize PMOS, and this can give me a CMOS inverter action directly. What we have used over here, we have used metal silicides in source and drain. We haven't used, see here, we haven't used any doped structure. This is metal source, this is metal source. So erbium silicide has been used in N mode and platinum silicide in P mode. So now if we compare this with the state of the art, this is the conventional structure. This is the conventional structure for the CMOS inverter. And this is our structure. Now compare the transistor count here, it is 2. In our case, it's 1. Junctions has got significantly reduced from 9 to 3. Junctions consume a lot of power. So see, 9 junctions, 3 junctions. So we can have power reduction by 3. Number of doped regions in the conventional here, this is the conventional 8. In this case, we have just 1 or 0. We can have this undoped. Number of substrate in the conventional 2, 3. Here we have just 1. So this is what this single transistor is all about. So I will not explain the operational mechanism. Now the thing is that people may ask question that with the doped structures, with the conventional doped structures, we can realize this inverter. We have proved that with the conventional technique, by doping, by merging, just folding the conventional, for example, AND drain dope and source dope, doped drain, doped source in P mode and N mode. We can realize this single device. No, not at all. The reason is that between this N doped drain and P doped drain, since this is, doped semiconductor, this is doped semiconductor, we can have the creation of the depletion region over here. This depletion region will stop the conduction. We actually need a direct conduction from this N drain and P drain. They need to be in contact, close contact. So depletion region in between cannot give us a close contact. So we have this electric field and we have this potential barrier over here. So this proved that a conventionally doped transistors, if folded, cannot realize inverter action break. So with this technique, we had realized a structure. You must be knowing about transmission gate, right? We use a gate which is being called as transmission gate, which actually allows controlled transfer from one port to another port. So we have realized that transmission gate by a simple structure. So what we did, so okay, so this is a structure which has directly realized a transmission gate. Now, if you see the conventional transmission gate, this is the conventional transmission gate. We have used separately NMOS, separately PMOS, and connected them, right? So this type of structure has been realized by this one. If you see the difference between the inverter and this one is that we have actually removed the oxide over here. We have drain and drain, metallic drains in contact, close contact. This is what we need. Metallic sources in contact. This is what we need in a transmission gate. But we have a controlled transfer. At the top, we have a controlled transfer at the bottom. Okay. Since in the transmission gate, we need NMOS and PMOS should conduct simultaneously. They must remain in on state simultaneously. They must remain off state simultaneously. So this is what we have achieved over here. So there are two transistors. A cascade of two transistors have been realized by one transistor. So these are the this is the saving. This is the comparative analysis. A lot of saving is there in comparison to SSS technology based transmission gates. Okay, so no operation, no discussion on the operation. Okay, this is again the transmission gate. This transmission gate has been realized by combining the SSS based inverter and SSS based transmission gate. So these two structures, just two transistors, have realized a complete transmission gate. So over here we have a 50% reduction in the overall size. So now we have realized
So
device. If you still count
Sadat Lone.
and again an AND gate. This is what I want to share. This is important. This is being called as gate engineered based devices. This concept actually gives us highly compact. This gives us highly compact structures. If you see here, this is a NAND gate in the conventional technology, right? In the conventional CMOS technology, we need 4 transistors, 2 in the pull up, 2 in the pull down, 4 transistors. But over here, we need just 2 transistors. Gate engineer, just play with the gate, design the gate, we can realize this. This is again for a NOR gate, 2 transistors. In the conventional one, 4 transistors. In the proposed one, just 2 gate engineered. Okay, but this doesn't look attractive. Here, this is 4 and 2, 4 and 2. This looks normal. But this is something different. Now, if you see here, we have exclusive OR gate in the conventional technology. Count the transistors. 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 transistors in the conventional exclusive OR gate. But in the proposed gate engineered technology, we have just two gate engineered transistors, 1 and 2. Right? Now the thing is that if we have more and more transistors in series and parallel, just we can have two transistors. Just play with the gate. So we can have multiple number of gates over here. We can have multiple number of gates over here. The multiple number of gates here and here at the top and bottom can actually create a structure which has been conventionally realized by dozens of transistors. Now in a Boolean equation, we have dozens of gates. It means we have hundreds of transistors. We can simply use, remember, Boolean equation, dozens of gates, hundreds of transistors. We can simply use two transistors, right? One in pull up, another one in pull down. So again, we have used another concept which is being called as hybrid doped MOSFET. So in this hybrid doped MOSFET, we have used conventional doped and we have used, the charged plasma type of things. Again, the objective is to realize, single transistor based gate, single transistor based hybrid blocks. And these are the advantages which we get out of, these structures. We have got highly suppressed devices. It means the magnitude of the short channel effect in these devices has got significant. This is the red one. This is hybrid dope. See here, the VTH roll off, it has got improved significantly. On the other hand, the conventional one, we had a drastic increase. Now the thing is, this is what is something different. Again, we have realized here a NAND gate. Earlier, we have realized the same NAND gate by using multiple transistors. But if we use this type of technique, here, hybrid doped with gate engineered. This is actually the combination of hybrid doped and gate engineered. With the hybrid doped and gate engineered, we can realize a NAND gate, we can realize an AND gate by just single transistors. See here, a single transistor realizing a gate which conventionally is being realized by multiple number of transistors. So significant increase. Significant increase in the packing density. Significant reduction in the space requirement. Okay, so this was all about the multifunctional devices. Now, what is our objective? The objective is again to have devices which can keep Moore's law valid and valid. The objective is to have a compact design. The objective is to have energy efficient designing. So we have different strategies. We have different, methodologies which we follow. With the first one is better architecture. Better architecture means we can go multiple gates. We can, for example, we have FinFET. We have, double gate MOSFET. We have other structures. So if we go for the better architecture, we can keep this Moore's law valid and alive for around 5-7 years. But if we go for better materials, most of you people are working in the material level of abstraction. So if we go for the better materials, we can design and develop devices out of these better materials, which can keep Moore's law valid for around 2 decades. Better materials means we can go silicon nanowire, we can go CNT-FET, we can go strained silicon germanium. But with these structures, with these materials, they have their own limitations. But if you want to keep Moore's law valid for more than 2 decades, we can go for new physics of computation. We can go in the new physics of computation means tunneling transistors, tunnel device, neuromorphic computing, reversible computing, right? So if we go for these, newer computational methodologies, we can keep Moore's law valid for more than around 2 more decades. But if we go for the multifunctional devices which can directly realize Boolean equation and higher gates, we can keep Moore's law valid for more than 20 years. So this is why the multifunctional concept is important. And again, what is the target? I mentioned that the transistor count in ICs. In the state of the art, IC is 12.9 billion, 19.2 billion in ADM's processor. And in the state of the art Core i9 Intel processor, and the state of the art processor Core i9, the transistor count is 7 billion transistors. Okay, so we have realized processors with billions of transistors.
Hello. Hello. Sajad sir. Hello. इंटरनेट खराब रहा आज.
Yes, sir.
हेलो. इंटरनेट का आज बड़ा प्रॉब्लम रहा. कुछ पार्टिसिपेंट्स लॉबी में हैं, उनको एलो कर लो.
जी जी
निकलेश.
कर दिया सर.
निकलेश,
जी
कुछ
सर.
लॉबी में हैं, कर लो. ठीक है. सजाद साहब, हेलो. हेलो.
Lot in terms of technology to actually reach to even 5% of that complexity, of that structural density. So let me conclude. Objective is to keep Moore's law valid, so we can work at device level of abstraction to have smaller and smaller devices, but we do have problems. The problems are in the form of short channel effects. Some of the well-known device structures, novel device structures, are PGP structures, partial ground plane devices, channel structures. But the multifunctional devices are the best choice. We can have triple S technology, we can have multiple gate technology.
Hello, Sajad sir.
This is
Hello.
all about lists. Imperfect cases are object optimized. Yeah.
Thank you, sir.
Hello.
I can hear you. Yes. Yeah, I can hear you. I can hear you.
Sir, your
Dr.
voice.
Shah, I can hear
Sajad साहब, take few.
I can hear you.
Take few. Take questions. Take few questions. Next.
Okay, sir. Okay, sir. Sajad sir, the first.
Yes.
Take couple of questions.
There are a few of questions from the participants.
Sure.
Sir, the first question is from Abhishek Bhapkar. When Apple and Samsung say 7 nanometer processor, what does it mean?
Well, see, when we say 7 nanometer, it is the technology node, right? The technology node in the conventional technologies. I mean, when the technology node, first I will tell you, conventionally the technology node was actually the channel length, right? It was a channel length. It was a separation between source and drain. So conventionally, we can say the distance between the source and drain is the technology node. So if they say 7 nanometer process, it means 7 nanometer technology node. So conventionally, it is that source and drain separation. But when we have crossed that limit, when we have crossed that, 0.35 micron, the definition of technology node has got changed. Earlier, it was true that technology node is same as that of the separation as that drawn length, but that is no more valid now. Okay.
Okay, sir. Okay, sir.
So 7 nanometer is the technology node.
Okay, okay, sir. Sir, next question is from Payal. Sir, how to make transparent solar panels using nanotechnology?
How to make
Transparent solar panels.
well, see, I am not from the field of solar technology, solar engineering, and I am not working in solar domain. So I don't know how to make transparent.
Okay,
So I
sir.
think the material scientist can answer this question well.
Okay, sir. Okay, sir. Sir, next question
I'm
goes.
a device designer. See, I'm a device and chip designer. So
Okay,
proceed.
okay, sir. No problem.
Yeah.
As we know, 5G technology is harmful for Earth. So, what we made to reduce its side effects? What can we do to reduce its side effects?
What can we? Okay. So people are saying that 5G is harmful, but if we see that in advanced countries in China, they have already tested the 5G thing. So if we see if we see that it is high frequency means high energy.
Yes, sir.
So high energy is always harmful. So the thing is that if it is harmful, we have to keep transmitters away from, for example, the area where people live. See, currently you see transmitters everywhere. You see mobile towers everywhere,
Yes, sir.
isn't it? We have mobile towers even on our buildings. But if the radiations are harmful, so we have to keep these. First thing is we have to keep these transmitters away from the locality. This is what we can do.
Okay, sir.
This is one of the solutions, right? And another solution is what I think is to have more and more isolation, or we can say that have more and more absorption. So we must work on absorbing things, absorbing these radiations. So if we try to design and develop devices which can absorb these harmful radiations, like see, we have a lot of UVs coming from outer space, and we have ozone. Ozone is absorbing, and we are receiving, we can say, better radiations. The same concept can be used in case of 5G or in case of NG things, if the radiations are harmful. But if the radiations are more harmful to the life, I think we should not then go for 5G and 6G and other Gs, because human life is more important than the electronics world. Can you hear me?
Yes, sir. Yes,
Can you
yes,
hear me?
yes, yes, sir. Sir, there are
Okay.
a few more questions, but due to the timing issue, I'll mail you
Now you can
those
ask me. You can
questions.
ask whatever you wish. You can
Sir,
ask if you.
so we have a next session also. For that, the timing is 12, so it's 12:11. So I'll mail you all the questions, and you can
Fine, fine. Mail me all the questions. I will gladly
revert back.
answer.
Okay, sir. Okay, thank you, sir. Sir, I would like Khushbu Iqbal to say thank you for Khushbu.
Thank you. Thank you very much, sir, respected sir, for such a nice session. You really enlightened us with your concepts about semiconductor devices. I am sure that many participants must have been served with knowledge by your session. Thank you for your time, sir. Thank you.
Thanks a lot. Thanks a lot. Okay, Ashraf Sahab, should I leave?
नकलेश हाँ खुदा के हवाले सजाद साहब
Okay, okay. Thank you. Thanks a lot.
we will formally thank you. We have our honored guest, Professor Sharma Saab waiting. So, who is a collaborator of this program?
Okay, okay.
So we'll be taken to task if we will deviate anything.
Okay,
So
okay.
it's all good,
Then,
sir.
sorry for taking a few more minutes.
No, it's all right. It's
It's
all,
okay, sir. It's
it's
okay.
all
It's
right.
totally fine.
Sajad Saab and Sharma Saab, both of you are in Delhi, so you can take it. Sir, please, Niklesh, invite
Okay.
Sharma Saab,
Okay.
please.
Okay, sir. Okay.
Please.
Khushbu, are you there?
Hello.
Nicholas, you can give me the sharing rights.
Yeah, for sure, sir. Sir, just a minute. I need to give a formal
Please.
intro.
Salman, ठीक हो आप?
That you have already given on the first day, so I think we can skip that. Just give me the share time and we will start.
Okay, okay, sir. That will be also okay.
पहले दिन बोल दिया यार बार-बार क्या बोलेंगे?
Okay, okay, sir. I'll give you the rights.
So good afternoon, everybody. In fact, so my aim is to talk about some fundamental concepts in semiconductor crystal growth and epitaxy. And this is primarily a sort of short tutorials for students, not for the experts. But what I wanted, and I'm trying to do in the country at various forums, is that to introduce a few concepts so that the students understand whenever they pick up the research in semiconductor material development, they already have the basic concepts. So I'd like to just mute my video so that, you know, if there is an internet problem, it will be easier for you to.
Okay, sir, for sure. Sir, there in the near to the mute option, there is a stop video.
नहीं एक्चुअली ये पूरा मुझे बड़ा करना पड़ेगा ना इसमें
Sir,
it is the view is different, so what I will do, I'll go back.
sir, can you see the stop presentation?
Stop present. You are okay. Pause, assign, mute, stop video. Okay.
Yeah.
Good. Oh, that's fine. So I think it will be easier for us to. How can I remove this screen? Okay, it has gone now. Okay, good. So what we will be talking about primarily is the bulk crystal growth on a larger scale rather than the nano pipes, etc., or the nano tubes, etc., or the any nanostructures. And that a similar talk will be given by Professor Jagdish tomorrow if he's coming over. So let us move. So what we will be doing is that we will be very briefly looking into the semiconductor materials, a little extension of what Professor J. Kumar talked about in his first talk. And a bit of the thermodynamics, what are the thermodynamical concepts which are important, a bit of phase equilibria, and then talk about nucleation and growth, the growth mechanisms, which are general mechanisms, and some techniques of bulk growth and epitaxy, just as an introduction. Since the time is limited, we'll try to rush a little bit, but at a later stage, anybody who has any questions either can ask those short questions after the talk is over, or he can write to me on the mail, and then I will try to reply. We can have a one-to-one interaction at any point of time. I will apologize that my talk is not very well organized, as I put together it yesterday from my coursework which I do at IIT Delhi in a special topics. Because of a little bit fatigue I have in my post-COVID recovery. But I hope I will try to connect the things, the dots, to my best of my ability. So what are semiconductors? The question is asked to postgraduate students many times that what are semiconductors? Which materials, what kind of materials are called semiconductors? And generally the answer would be, something between insulators and conductors. The conductivity should be in between. Somebody would say that, okay, the band gap, which is around 1 electron volt. But all these definitions, in fact, do not cover all the, I have given a huge list of semiconductors, and the conductivities will vary from that of metal to the insulators, maybe sometimes better than the known insulators. And the conductivities also are very, very high in certain cases. And similarly, the band gaps can vary from 0 to 6 electron volts. So virtually from a metal or a semi-metal to an insulator. Like the diamond is also can be is the best insulator we know, but this is also the best semiconductor for making say very high voltage devices in future. So, since you could see a list of so many compounds which are semiconductors, and we will see why they are semiconductors and what is the criteria when we say that this material is going to be a semiconductor. And so, look at the group 14, where we have silicon, germanium as the known semiconductors. And silicon is the ruling the semiconductor arena, but then the gallium arsenide or indium antimonide, indium arsenide, gallium antimonide, similarly cat telluride. That means that what we are trying to do here is that there are 4 outermost electrons per atom, and then if you mix 3, 5 or 2, 6, and sometimes 4, 6, depending upon what kind of bonding we have. So we can have say materials from 2p or say 1a, 1b also being used for making all these semiconductors. And you can very well see that if you have this compounds formed in this range, they will be largely covalently bonded. But if you are having something, say, a compound formed from this area to this range, that is up to 5th, 6th, 7th A and 1st and 2nd A, as well as some of them in the initial B blocks. You'll find that they largely become ionic materials, and they do not fall in the category of semiconductors. So eventually, we can now look at all this and then go back and, in fact, look at our earlier list and see that how many kind of semiconductors, how many materials would behave like semiconductors, and why do they do? Primarily, let us look at the energy bands in silicon, and what you see here is that the 3p and 3s orbitals make hybridized orbitals. This is given sp3 hybridization, and with that you form bonding as well as anti-bonding orbits. And if you join all these orbits, say if you have large number of atoms, and so what happens is that there is a band of energies from bonding orbitals as well as anti-bonding orbitals forms. And what happens is that the bonding orbitals give you the valence band, because the electrons would like to stay there all the times, particularly at very low temperatures. And then the conduction band is formed with anti-bonding orbitals. So this is how chemically a semiconductor is going to be stable. So this is the primary criteria, and basically, this is where we have to look at if you want to see a material being used as a semiconductor. So we have seen that could be semiconductors could be elemental or compound, and then we know that they can have multiple type of carriers. You have been listening to this for quite some time, and there is a band gap between valence band and conduction band. Okay, so and then you have concepts of direct band gap semiconductors and indirect band gap semiconductors. And direct band gap semiconductors are useful for optoelectronic devices where the photons can freely can get either absorbed or say emitted with a band-to-band process, electron-hole recombination. While in indirect band gap semiconductors, you need a phonon to assist this process, and then the optical processes become very, very inefficient compared to the direct band gap semiconductor. That's why people, the other kind of materials like gallium nitride is a household material now as a LED light sources and so on. So we are not discussing it, but these are the concepts which are important and should be properly understood when we venture into the semiconductor materials research. So, Professor, Professor Jayakumar has shown you these figures, and I'm not just scanning through. There could be variety of 3, 5, 2, 6, and all sorts of materials. But compound semiconductors, which are direct band gap semiconductors, in fact, have been utilized quite a lot because of their capability to give you quantum heterostructures, and which the photoelectronic devices, as I mentioned earlier, and they possess higher mobility. And then here this figure or the other two figures show that you can vary the band gap by changing the composition. For example, in case of the rightmost indium arsenide, indium antimonide, the band gap can vary from about in this particular range, and then similarly, you can have a lattice masked situation with gallium antimonide being lattice masked to indium arsenide antimonide, where indium antimonide is very small, about 10%, and so on. So these diagrams are very interesting and very important to understand when you want to do semiconductor crystal growth or epitaxial growth. Why do we need epitaxial structures? We perhaps will see slightly later. So a basic concept is important, and as we know that the Gibbs free energy is an important parameter for thermodynamics, and so what happens is that all the states, for example, if you want to have an equilibrium state, as we know that the free energy has to be a minimum in that state, and that means that any deviation is greater than zero. So that means that if you try to, for example, this is a system where there is a variable and the free energy is plotted on the y-axis, you have a minima, and around that minima, if you try to see that always the delta G is going to be positive, that will be higher. So that is the prime criteria. And then there is the concept of chemical potential, because many times you need equilibrium between various materials or the phases of the same material. And then for that purpose, the chemical potential is an important parameter, which gives you the free energy per mole of that component in any material. And in simple terms, the chemical potential can be defined as a chemical potential in a standard state, and then a correction factor with as an RT log P, if you know the pressure, partial pressure of that component, or if that component is in the vapor form, or if it is in the solution form, this should be RT log CI, that is the RT times the log of concentration. And then there is a term called activity. Sometimes they deviate from the with deviation from the pressure because of the interaction between various atoms. So if in a highly concentrated material, this cannot be truly true, because all these expressions are only true for very dilute solutions and very non-interacting gases. So there is a correction factor called activity factor, and then you can still have similar kind of expression, and then try to understand the basic thermodynamical behavior of the material. So what you need to do is to then understand that you have to have that if two materials are in equilibrium, then the chemical potential of the same component in the two materials, for example, here there are the same material in two phases, liquid and in solid. So what you can see here, that it is not necessary that the solid which is in equilibrium with liquid, will have the lowest free energy. But what should happen is that since this is the graph of composition versus free energy, so what happens is that what you need to do is that deva G by deva X, or the Ni as we told earlier, that is the chemical potential, should be same in the two materials. Then only the material will not go, will be in equilibrium, or will not move from one phase to the other phase, else it will move from one phase to the other. Like if it is, if the free energy of solid is higher than the free energy in liquid, then the solid will start melting, and vice versa. Okay. So let us talk about in terms of chemical potential. So this is important for us to understand that the chemical potential is a very important parameter, and whenever you have to look into stability of a system, you should go back and try to see in the form of chemical potential. A very important parameter, which is also utilized in semiconductors to control the non-stoichiometric behavior or the deviation stoichiometry, is similarly the chemical equilibrium law of mass action. And if I have a chemical equation where, for example, in this case, A solid and B solid react into form another material C, which is solid, and they also have another component D as a gas. This is given an example. Then what you can do is that you can find out that the activities raised to the power their fraction is divided by the product activities is a constant as a function of temperature, which is a function of temperature of course. So this is a very important parameter and very easy. This is the equation which guides you how to control the stoichiometry of a material, because the semiconductors are very, very sensitive to non-stoichiometry, because the vacancies, interstitials, antisites, all are electrically active. So they will they will contribute to the conductivity. So if you want to have one kind of conductivity, you will have to, in fact, control the non-stoichiometry. The non-stoichiometry we'll see a little later if we have time. But just I wanted you to give a bit of an indication how thermodynamics helps us in understanding. There is another very important rule called the Gibbs phase rule. And, without going into the details or, so what we understand here is that the degree of freedom in any system can be given as the number of components C minus the phases in equilibrium plus 2. And we are not looking into the how it has come, but let us assume that. And how it is important is that we have to see. So then another important concept in understanding, or say before you can start any crystal growth, is the phase diagrams. And why we are seeing how they are constructed is that how to, in fact, say understand what are liquidus and solidus. So for that matter, for example, let us try to see what happens in case of when we plot the free energy as a function of composition in any material. So what we find is that the free energy, for example, in the solid behaves as a green line, and that in the liquid behaves as a red line. So what we can understand for a particular temperature, Tm, or whatever temperature we are looking at, why we have put Tm is that we will see. So at the melting point, for example, the free energy or the chemical potential of solid and liquid is same. So material, both solid and liquid, we are talking about a one component system. So it is in equilibrium. But if we go to the two component system also at this end, that is at the origin, the composition NB is 0. That means it is a pure component. So for a pure component, what you will see is it is same. But then At various compositions, what you see is the free energy of solid is higher than that of liquid, and eventually you can draw a lot of diagrams, and on the basis of that you can construct that okay, the liquid and solids of at the same temperature will have the same chemical potential for different composition. Like this is the diagram in which this is the equilibrium. Say above this line, the material remains liquid because of the fact that the whole thing. For example, here, if you look at this will remain liquid beyond this point. If I move at TMA and move into any composition, liquids free energy or the chemical potential is low. So this whole region will remain liquid. You can have any composition. This will remain liquid. And similarly, below this line, all the composition will remain have solid, and that is how. But in between, as you see here, there is a point where the chemical potential in solid is also in equilibrium with chemical potential in liquid, and that is where we are having this liquid in equilibrium with this solid. So that is the basic, the fundamental reason why these diagrams are constructed, and then you apply the Gibbs phase rule, and then it simply gives you, looking at the phase diagram and looking at the components, etc. You can just look at the phase diagram and try to see how we do that. So just to many systems are what are called isomorphous component systems. That means if you have gallium arsenide and maybe cadmium telluride and say zinc telluride, you will have this kind of a diagram. Maybe the zinc telluride here and cad telluride here, and then you will have a forbidden region in between. That means that no composition within this range is stable at all. That means that at these temperatures as well as these concentrations, what you will have, for example, if I have this composition, that means suppose this given by this line over here, and this is the temperature T0 which I am looking at. So this composition is not stable. It will be a it will be a combination of some liquid and some solid, and these liquid solids are governed by their concentration is governed by these lines. That means this is the liquid concentration, this is the solid concentration, and their respective amounts are governed by what is called a lever rule. Very simple. Say if it is closer, it will be higher. It is far away, it will be less. So that's why it's called lever rule. So we have to apply the lever rule to exactly find out what will be the respective concentrations. So this is useful when you do the crystal growth activities when from the melt. But similar diagrams are possible for vapor to solid, and in the same manner, this is this was what is called isomorphous system, in which you have complete solubility from A to B, and there could be another system in which you do not have solubility from A to B, so you will have a limited solubility of B in A and limited solubility of A in B. So this is important. Both are solid. This is also a solid, but you have a limited solubility of B in A. That means that the solid A can have some amount of B contained in it, and that is again due to the free energy criteria. We are not going into that. You can very easily understand that. So, but then you can see that this is the same type of diagram which we saw earlier. It could have gone like that. It has not gone. So the liquid remains stable above this, and you have a minima in the liquidus, and which is called the eutectic point. And so if you have this liquid composition, and if you try to freeze it, you will have this solid as well as this solid. So it freezes into two solids. And in metallurgy and metal systems, this is very common. Solders, etc., semiconductor people also use it. But in semiconductors also, in many cases, this is important when you do what is called liquid phase epitaxy. Then you can have very, very important systems where a component A and B form a compound AB. And then the compound AB also will have a limited solubility of A in AB and B in AB, but there will be a limit to that. As we saw that there is a limited solubility of A into B, as well as solubility of B into A. So this green line over here gives you the saturation of A with B. Red line gives you otherwise B saturated with A. And this is the main alpha phase, where the left-hand side gives you the AB material saturated with A, and AB saturated B is on the other side. That means that is what non-stoichiometry, or sorry, the stoichiometric deviation I was talking about. This could be very, very small, right? It could be, say, delta value could be very, very small. And that is again due to the chemical potential variation. We are not looking into that. So basically, you can apply the law of mass action. And for example, if I have mx solid in equilibrium with its gas, say M metal gas and the non-metal dimer gas, which is normally a case, for example, for cadmium telluride, where you have cadmium atoms independent, cadmium and tellurium 2 gas. So you can very well apply the law of mass action, which I told you earlier. And then what we see is that there is a interesting relation, that the pressure of metal, or the M component, multiplied by the square root of the pressure of X component, is a constant at a particular temperature. That's very interesting, and that is where, in fact, this gives rise to a stoichiometric deviation in the material, that in the form of delta. This delta could be very small in some materials, it could be large in other materials, and for ternary and quaternary materials also, you can have similar kind of. But this is a very, very interesting and important concept when you are looking into the crystal growth, particularly when we are doing from the molten material, that is either from the melt, which is the stoichiometric melt, or from the liquid phase epitaxy, where we see we can have a solution. So in all these situations, how to control this delta, it becomes important. And similarly, that means that you can also control this delta by changing the vapor pressure over there. For example, if I have a X-rich condition, that means that Mx is 1 plus delta, and if I can increase the pressure of M component at a particular temperature, so I can drive M atoms into this material, and then it can ultimately become Mx1 minus delta, depending upon what we want to do. So this is a possibility of, say, equilibrating your semiconductor or the compound semiconductor material with a known pressure of metal or non-metal entity, or either of the components. And these parameters are very well known. These are for example, it is the enthalpy of formation, etc. These are very well known parameters you can find in the literature. And then, but you have to understand and utilize them, and they're very widely utilized. These are various kind of phase diagrams. This is for gallium arsenide. I'm not looking at some, just flashing because of the paucity of time. We have to move for other materials. And similarly, ternary diagrams can also be formed. And these ternary diagrams, in fact, they can be what is called pseudo-binary diagrams. For example, in case of mercury, cadmium, tellurium, here I can form mercury telluride at 50%, telluride at 50%. I can see that this is the diagram for mercury, cadmium telluride. And similarly for mercury and tellurium, I have a diagram like that, where the mercury telluride is forming over here, and there is a eutectic over there, and so on. So similar diagrams are used and are useful for when you do the crystal growth. Well, this we are not looking into. So the next concept which is important is the driving force for crystallization. And as you know, we can very well understand that free energy of a solid is minimum in the crystalline state. You can very well understand that if you have non-crystalline material, you have a lot of boundaries, you have a lot of defects, and they will contribute to the so I'm talking about extended states, but if you have some point defects, the free energy can go down a little bit. For example, over here, what we have seen, point defects induce randomness, and because of the entropy is increased, so your delta G could be low. So what happens is that thermodynamics in fact favors point defects, but to a certain extent, because then the delta H is also important. If the enthalpy of formation of the defect overcomes the delta S factor, then it will stop its solubility. So it's very simple, but you have to look into that. So, but eventually the dislocations, tightening faults, gain boundaries, etc., and similarly amorphous and glassy states. So, okay, this is a question I asked my students, and you can also go back and try to look into this question. So, can nanoparticles be free from point defects? So, this is an interesting question for students. Look into it, and then you enjoy its answer. So what happens? The process of solidification and condensation, either it is say solidify from liquid to solid or condense from gas phase to the solid. So what happens is, from a completely disordered state, you go to the ordered state, right? And but then what will happen? So from completely disordered state, how do you come to the ordered state? So the process will start with formation of atomic or molecular agglomerates, which are well arranged, and then it will grow, and we'll see how it happens. So what happens is, even if you make a small thin film, say deposit a vapor deposit a film on a substrate, you might have seen that it has a lot of micro or nanocrystalline materials. Making an amorphous material becomes almost difficult for all the materials. There are only some materials which like to be in amorphous state because of certain reasons we are not discussing today. But if you try to deposit zinc sulfide, zinc selenide, or some such materials, they try to become crystalline. And why they are micro or nanocrystalline, you will understand once we start discussing how the crystallization will take place. So well, again, as we have seen, for crystallization also, a similar kind of condition has to be looked into. And then what we see is that the crystallization of a liquid into solid would require some sort of a what is called a temperature difference, which is called supercooling or undercooling. And similarly, with the concentrations or compositions in a solution, it is what is called supersaturation. So you need a liquid to form. Otherwise, liquid doesn't form convert into a solid exactly on its melting point, only because of the reason of the randomness being given, being available in liquid. So the free energy because even at lower temperatures, this delta S overcomes delta S, it doesn't freeze. So with a very simple arithmetics, you can find out that you need some sort of a supercooling to freeze a liquid into solid, which is a crystalline material. So, well, so the general condition, as we have told you, should be that chemical potential in solid should become below that of a liquid or a vapor for solidification or condensation. And a very simple condition comes out that this delta mu comes out to be delta P by P. That means that the pressure difference, that you have a higher pressure, a limit of higher pressure, or the higher concentration, which is called supersaturation, which is related to the what we have seen as supercooling. So what you need to do is to have a melt should be supercooled, or a vapor or solution has to be supersaturated. Similar things, not much different. I would like to tell you that why I am putting these things together is that they have a similar idea behind it, that you need to have the chemical potential in solid lower than that in either liquid or vapor, where from you are freezing or you are condensing. So, and in the same manner, you might have the kinetics, in fact, depends on various factors. But again, higher the supersaturation, faster is the kinetics of. So what you need is that we understand from vapor also, there will be atoms will come closer to each other, and then go away because of the kinetic energy or the thermal energy, but some agglomerates will form based on what kind of supersaturation you have. And there also the concept of homogeneous and heterogeneous nucleation, because these nuclei, in fact, if they form independently in a liquid, they could be considered to be small spheres, and then you can have an idea where say you have a critical radius of those spheres, after which the free energy starts falling if you grow them. So they very quickly, but initially it increases. So with the statistical randomness, some atoms will come closer. They will form a critical radius, and once they form the critical radius, after that, adding more atoms is more useful to them, and then they start growing. So that is how homogeneous nucleation will take place. But most of the times, it is heterogeneous. This is what we want to do. For example, if you have a substrate, any substrates, or even if a nuclei has formed and it has become big, it is a heterogeneous substrate. Okay. So once it is formed, after that, in fact, the total amount of surface energy which in fact forms is less compared to the surface energy of a pure sphere, as you can see over here. And then there is a lot of advantage. As you can see, for the homogeneous nucleation, the total free energy requirement delta G is much higher than that for the heterogeneous. So the heterogeneous nucleation takes place much easier than the homogeneous nucleation. And I just told you, once you form a big nuclei, it is more or less a heterogeneous nucleation later on. So there is not much difference. So even if in a crystal growth, a crystal has started forming, initial nucleus, initial small crystal has nucleated, and after that, it becomes a heterogeneous. So the next thing important is that we should understand how the crystals do form, either from a melt or from a I think, can we take another 20 minutes?
10 minutes, sir. Sir, 10 minutes, sir, okay? Sir, 10 minutes.
Well,
Sir.
let me see.
Yeah, sir. Because people have to go for prayers. It's Ramzan, people have to go for prayers.
No. Then I will stop, and then we can have another session some other day.
No, it's all right, sir.
No, I'm not stopping here, but by 1 o'clock I have to stop. Okay.
Yes, sir.
No, I just forgot. So anyway, this is important to understand that on any crystalline surface can be, in fact, cannot be a perfect match to any crystallographic orientation. For example, suppose 111 in a which is a close pack surface. But there will be some deviation of a fraction of a degree or a few arc seconds. So what you will have, that all the surfaces all the times will have lots of defects like steps. There will be edge vacancies, or some units, independent atoms, or units sitting over there, or independent surface vacancies. So all such things would be there. You can see this is how atoms are. So you have a surface vacancy over here, you have an edge vacancy here, independent atoms sitting over there. So you can imagine when atoms come on a surface, they sit like that. Okay. And so this is Kosel's model of a crystal surface, which is important for us to understand. So what happens is that in such case, what you can see that whenever atoms come to the surface, they will be absorbed at the surface. But if you have a structure like that, the growth will take place in a way that all the atoms will keep coming and adding at edges or the kinks. And why it happens is that if an atom is sitting over here, you can see it has 5 free surfaces, while if it comes and sits over here, it has only 3 free surfaces. Okay, so because of that, it will require less energy. So atoms would like to, if you allow them to migrate over the surface, that means provide them sufficient temperature, which is called adatom mobility, sufficient adatom mobility, then they would like to come and continue to sort of extend the crystalline arrangement. And you can see that the whole layer can form, then another nucleus can form and then start growing. So this is a very interesting thing. This was called KSV model, and that is a majority of the crystal growth, either epitaxial or bulk growth, takes place through this mechanism. So we have to understand this. This is important, and so there's not much difference. Let us look into it. And there's another important aspect which Professor J. Kumar talked about on the first day: use of, say, requirement of or the role of screw dislocations. Which Professor Ajit Ram Verma, Dr. Ajit Ram Verma was the one who first, discovered using simple Nomarsky contrast microscope. Okay, so and that is where the thinking had changed, and what you can see that in a screw dislocation you have a step on the surface, and then atoms can come, and then in the form of a screw the crystal growth can keep on happening. There is no requirement of fresh nucleation all the times. So the screw dislocations in materials say help in faster crystal growth. So this is very important. We'll look into that. Then there are crystal growth modes. I'm skipping, but you can see a beautiful pictures which show you in the same material step growth as well as a screw dislocation based spiral growth. But you can see this is much higher than this because the it doesn't require nucleation of newer growth structures. This is a silicon carbide, which so I just put it here because I thought I'll show you interesting pictures of silicon carbide with using screw dislocation. This is the TM picture which confirms. So with this, I think what we can understand is that in an oriented crystal or what we call a seed crystal in a crystal growth structure, you can have a supersaturated vapor or liquid, and sometimes a solid to solid growth also can happen, which is called solid state recrystallization or solid state drain growth. But you can understand this is a high chemical potential region, this is a lower chemical potential region, so the atoms try to migrate over here, and at a definite temperature they will keep on moving on the surface. Say once they come, they add to the surface their energy, because one, they attach to the surface, surface energy goes down, they become more stable, and then they start moving on the surface, and then they will form a transition layer where the concentration will be little depleted. It can be, this transition layer is very important both in solid as well as in vapor, but this is, we are talking about equilibrium growth. If it is direct growth like MBE, then it is much easier. There is no transition layer virtually. But still in those cases, there will be some atoms which will re-evaporate in the region closer to this, and then there would be a transition layer. So this is also an important aspect. You have to consider this. Then, the transition layer will remain and the growth will take place. So that is how, similarly for chemical vapor deposition, reaction takes place on the surface and similar kind of things happen. And another concept after which I will like to stop, because I will leave certain points for question. I wanted to talk about a few crystal growth techniques, which I think for the paucity of time, I'm not going to do today. So this is an important aspect that for example, for the sphalerite structure, it is a zinc blende structure. In 1-1-1 direction, or in 2-1-1 direction, or in 3-1-1 direction, you will find one kind of atom sitting on one on one side, another atoms sitting on the other side. And it is important to look at, because, and for example, in case of zinc blende in 1-1-1, so we call it 1-1-1A, where the metals are on top. For example, cadmium telluride, the cadmium is on top, and the tellurium atoms are on the top. This has repercussion for crystal growth. Similarly, for woodsite, like in gallium nitride, you have a cation polar or you have an anion polar on one side in 001, which is 0001 is equivalent to 111 for the structure here, except that it is AB, this is ABC. So this is an important aspect. And similarly, to sum up my talk today, a bit of misconception towards epitaxy has to be looked into. So what we see in case of various people calling thin film from fraternity that they are doing epitaxial growth, but semiconductor people want a single crystal as an epitaxial structure. For example, here what you see, there are a lot of columns. However, this orientation could be same in certain cases, which they call say epitaxial growth. But semiconductor people have a very different idea. They need the whole crystal to be oriented exactly in the same direction. However, if you look at the parallel to the surface, you will see domains either aligned in one direction or most of the times aligned randomly. But in case of semiconductors, the epitaxy in true sense means growth of one crystal on another. Growth of one crystal on another. Please understand. And that is where I think a lot of confusion takes place. But be careful when you are asked questions in any interviews or in any discussions. So you can humbly tell people that this is the situation. So with this, I think we'll not, I'd like to stop because we can have time for a few. I'll just flash my slides quickly and then stop my discussion. Okay, this is also an important point, like how the MOSFET dislocations form. And so I made one view graph in which you can see this is the substrate, and on that an epitaxial layer is growing. So if a dislocation is coming from the substrate, it will keep going up. But after a while, because the layer will be stressed, this will bend, and then you will form. Or another way is to form a dislocation from top. So this is a MOSFET, component. This is the component which is threading, which is called threading dislocation, is coming out of that. So these are the only two methods by which MOSFET dislocations will form. So with this, I think this is the Bridgman technique in which you have a temperature gradient. Another technique is Bridgman-Stockberger's technique, where you lower the crystal in a temperature gradient, and then there's Sokolotsky technique, as you can find out, and similarly vapor growth techniques. So with this, I think we will now move into my last slide. So thank you very much. I wish you all the best. There are a few books which I have left here. If you're interested, you can go to them. Thank you.
Thank you, sir. Thank you, sir. Thank you, sir.
Welcome. Welcome.
Thank you, sir. Thank you, sir. Thank you. We are blessed. We are obliged.
No, it's fine. It's my pleasure being with you and making this talk, which in fact, I thought it's important for students to have some idea about these aspects when they go for the crystal growth.
Everybody was doing it with the faculty development programs. I thought now our students are in a distress. Let's give them some inspiration that many more things can be done even after pandemic, the moment we will explore these times.
Yes, sure. So
many things in medical science have come up. Those are based on electronics.
Yeah.
Even minor.
No, medical means the most of the these polymer chain reaction chips and all these are because of the semiconductor technologies.
Yes,
because they are say all this system on chip or lab on chip that I was saying, and they don't require, say, you need to understand the concepts of semiconductor crystal, the device fabrication, and use them in a very crude manner, in a very, very simple experiment, equipment, and then make all these things, because you don't require them to go to nanoscale. A few microns is fine, and then all these small devices which are important for semiconductor. We are all importing all of them. We are not making them in the country, although we can do that. That's what I mentioned in my first talk. So I want students and faculty also who are interested, they should make startups and use their own wisdom to build small equipment. अभी क्या है कि हम इक्विपमेंट खरीदने जाते हैं, वो इतना महंगा देता है कि आपकी हिम्मत नहीं होती लेके लगाने की. तो आप बोलेंगे कि भाई you need 10 crore rupees to start a very small this thing, You need a mask aligner. You don't require a mask aligner. You can make a mask aligner in the country itself. And there is one
Right.
professor, Vinod Kumar Jain, who is a retired person from SSPL, and he showed us that if you want to make a device of 10 microns, use a microscope, and that's all. And it can be used as a
My Lord.
wonderfully used because as a mask aligner. So,
You are
and he's
right.
still doing a lot of work in MIT. He's been hired by MIT. He's got hundreds of patents with very
Oh,
simple devices. Yeah.
my
So I
God.
think, but you see, we have been good in making patents and publishing papers, but we should be good in technology. We should do something for
Yes,
ourselves, our people.
you are,
This is
you are
not,
right.
we are not doing anything for our people. We are doing it for us. So if we are publishing papers, we'll get promotions, we'll get recognition, we'll get awards. That's all. But what are we doing for the
For the
people?
people, for the people who
Yes,
are in a crisis, for the people who
yes,
are in a crisis.
yes.
A simple thermometer, sir. People are crying
Yes.
for a simple thermometer.
Yeah.
Yesterday,
Like-
somebody was crying for an IR thermometer. You just see, sir.
Yeah. But this IR thermometer is also not very essential for us to do. It's okay. But I agree, this could be made very cheaply in the country. What you need is
Yeah, this could be. That's what I'm saying, sir. It should be with everybody. Oxygen
Yes.
concentrator should be with every home. With every home.
Yeah. Yes.
With every home. We have a plenty of oxygen in the air. Why not to make an oxygen concentrator which could be there in every home, sir?
Yes. Very true.
This is what I have always been saying to my students.
No, that's
that
very
we
true. I
need
agree
that
with you.
technology should reach to the grassroots level.
Yes,
Then and
agreed.
only then people can be benefited by this.
Yes. So,
Niklesh, can you take few questions for sir? Niklesh. If sir, in the meantime, sir, if I request you, sir, the one your senior professor in SSPL, if he wish to speak for 5-10 minutes tomorrow, if you can give me his number, I can.
I think he is an expert in Dr. Bhan you are talking about. He is an expert in infrared technology.
Okay.
So he could have given a talk on infrared detectors, which are important. Okay, but I think he is a big professor. He needs 2 hours at least to speak.
10 minutes.
Then I have another Kashmiri, Dr. Dhar, and he is a legend in semiconductor physics. I will connect these 2 guys with you sometimes.
Okay.
And
yes, sir.
So Vikram Dhar is a legend, and so is
Vikram Dhar is in IIT Kanpur.
No. Vikram Dhar, in fact, retired from SSPL and is doing his own work. In fact, he has published a work on herd immunity recently. So he's a great physicist and great student. So
if you can give me his number, I can request him. That's how I can request.
हाँ मैं आपको दोनों का भेज दूंगा.
मुझे सर भेज दीजिए ताकि कल हमारा वो
कल तो आपका है दो लेक्चर है ना, उसके बाद भी टाइम है आपके पास.
कल 2 लेक्चर है, उसी के फौरन बाद 5-10 मिनट बोल लेंगे सर.
मैं भान को बोल दूंगा, पूछ लेता हूँ और फिर मैं आपको बता दूंगा. I'll talk to Bhan को भी. At least for, as you said, for the infrared cameras, infrared thermometer, if you can speak for 10 minutes, that will be great. It is.
Sir, that's very great, sir. I remember, sir, Rajesh, sir, I'm sorry to take the time of participants. So, I remember, sir, वहाँ पे एक वो हमारे गांव के करीब, I belong to north of the Kashmir. So, वहाँ पे वो लोग जो थे, एक बच्चा कहीं वो आया था, कहीं गेस्ट आया था, तो वो बेचारा डूब गया, नहाते नहाते डूब गया. So, it was sad. So, I went over there. तो एक वो थे बेचारे मजिस्ट्रेट साहब, तो उनको हमला किया लोगों ने. तो आई वेंट देयर, मैंने कहा नहीं ये मेरा क्लास फेलो रहा है, लेकिन सारी एडमिनिस्ट्रेशन वहां पे थी, उस बच्चे को ढूंढने में कुछ नाव भी लाए. Then somebody told them that there is a one IR camera, infrared camera. With the help of that, she was located in that nadi. So the importance of all these things. आजकल जो है नाव किश्तियां डूब जाती हैं, So it becomes difficult for the government to locate them. तो इनका बड़ा अच्छा रहा है. Regarding this IR thermometers, मतलब अच्छा रोल किया इस क्राइसिस में, इसने अच्छा
नहीं
रोल
तो
किया.
आप ऐसा कर लीजिए, कभी आप चाहें तो एक सेशन रखिए जिसमें इंफ्रारेड के ऊपर होगा, तो maybe we can have one day session in infrared, and people will talk about infrared systems, infrared cameras, and infrared materials, semiconductors. So we can have everybody takes about 1.5 hours, and then it could be a good session. मैं आपकी बहुत चाहता हूँ, आपको का एंथुजियाज्म इतना अच्छा लगा मुझे. देखिए, मैं तो हिम्मत नहीं है मेरी ज्यादा देर बैठने की, और आज भी मैंने सोचा था, तकिया वकिया लगा रखा था कि थक जाऊंगा तो लेट जाऊंगा, बट you gave me energy. I am still recovering from a very bad COVID infection, and
yeah,
so
may God bless you. May God bless you.
no, I will be slowly recovering, but this is a very bad. I suggest everyone sitting here, please avoid getting this infection. And it is a very silent infection. Sometimes, say for us, me and my wife, we did not experience anything apart from the fact that one day morning we started coughing very violently, and then when we suspected कोई बुखार नहीं चढ़ा, कोई तकलीफ नहीं, suddenly लगा कि अरे क्या हो गया.
And then also you do not know its origin, where from it has come out.
Yes, and then you never know किससे मिला, कहाँ मिला. और दूसरा ये कि आप अपने आप को आइसोलेट करो, घर से बाहर मत जाओ भाई, और डबल मास्क लगाओ. मैं तो हाथ जोड़ के सबसे बोल रहा हूँ, अपने दोस्तों से, अपने कलीग से, अपने स्टूडेंट से, भाई अभी 2 महीना आराम करो घर में, कोई बात कुछ नहीं होगा, कोई heavens will not fall.
Yes, heavens will not fall. Heavens will not fall. Heavens will. Sir, will you take some one, two questions, or will you see?
I am fine, but I think your time is.
That's all right, sir. It's all right. 5 minutes. Take one question or two.
No, anyone.
Naklesh.
I'm not hearing you. Nikhilesh, I'm not hearing you.
Niklesh, you are mute, probably. Niklesh, you are mute. I can take the questions even.
मैं देख लेता हूँ, chats में होगा ना?
हाँ सर, chats में होगा. Nice presentation, informative, wonderful. Thanks for impressive session. How can we select transparent conducting TCOs, sir, materials in solar cells?
Well, that is again a very specific questions, and depending upon that your base material, that whether you are using a silicon solar cell or a gallium arsenide based one, or 2,6 based, different materials are used. But what you need to do is to have a TCO which has a correct kind of conductivity as well as the correct kind of transmission. And then it should also have characteristics which where you can use them as what is called anti-reflection coatings. They should not reflect the material, the wavelengths which you want. So it's a bit complicated thing, but you can look into that. What you need to do, correct band gap, conductivity, as we understand that you can take conducting oxide, but then the refractive indices of the various layers have to be in such a way that the band in which your semiconductor detector is sensitive, it should not be reflecting back.
Sir, we'll end it there. We'll end it here, sir. But with this, with the hope that every home will get a solar cell, every home will get a solar power in future.
Sure.
We need to explore sciences that every home should have a vegetable garden, every home should have his own water, and every home should have his own solar power.
No,
they should be self-sufficient.
So you are lucky to be in Kashmir, where you have a lot of space and you can do. But in people living in Delhi and NCR, they are not that lucky. We live in very small cages, small cages, and but I agree with you.
Right.
Lot of vegetation is required in the country. Okay, so nice interacting with you. And in future, Professor Shah and Nikhilesh, whenever you want my support, I will be there. And I would suggest that why don't you have an initiative and then make certain members and institute a SSI
Sure, sir. Sure, sir. That will be, sir. That will be. We have many good students in NIT Srinagar. We have many good students who are lovers of this physics.
Yeah, no, I would say that please connect with the University of Kashmir as well as Jammu University and
Yes, sir. Yes, sir.
Vaishno Devi University,
Yes,
all these universities wherever semiconductor people are there, you take an initiative as a nodal center, and then NIT can act as a chapter which so we will have. I'll be very glad to have a Jammu and Kashmir chapter for SSI.
Thank you, sir. Thank you, sir. Thank you.
So you can assume yourself as a coordinator initially, and then later on we'll see.
Sir, in September, I wish you again. We are proposing a conference on nanotechnology for better living.
Okay, good.
So last time it was with IIT Kanpur, then it went to IIT Kharagpur. Now this year IIT Delhi is willing to join hands.
Okay,
so
great.
I wish you there also. I wish you there also, sir.
We'll definitely.
Yeah.
Okay.
Nicholas, say words of few.
No, it's okay. So you have already spoken quite a lot. It's a pleasure from my side. Thank you very much.
Shukriya.
Thank you. Bye-bye. Yeah, shukriya.
Nicholas, if you want to say.
Yeah.
Nicholas.
I think Nicholas' voice is not audible, so I will say vote of thanks. So I'm
Good.
Yeah. Hello, sir. I'm Mohammad Zubair Ansari.
My great one of my great colleague from IIT Delhi only. He joined in 2018. Sir. Mr. Zubair Ansari. He was with Professor Khere Sahab.
Acha. Oh, great.
Yes. Yes. Zubair, say please speak. Please speak. Please.
Just tell me. Not Khere sir. I'm my co-guide also Vikram Kumar.
Oh,
So he was the director of SSPL and also director for the NPL. After then he joined the IIT Delhi. That time I was joined the PhD. So
good.
Okay, sir. So I will say the word of thanks. So our most valued invited speaker of the day 4, Professor Amisha, organizer of the short-term course, distinguished delegates, ladies and gentlemen. I deem it a great privilege to propose a vote of thanks on the behalf of the Department of Physics. I would like to thank you, Professor Sajad Ah Lone from ECE Department, Jamia Millia Islamia University, New Delhi, delivered a wonderful talk on multifunctional nanoelectronic devices, a way to keep Moore's law alive. Professor Lone explained Moore's law in details and correlate with the transistor. Professor Lone discussed about the scaling of chips and correlate with the cost and energy consumption of the devices. It was really a very useful talk, especially for the master student and research scholar, those are working in the field of transistor. The second talk by Professor R.K. Sharma, Chairman of Semiconductor Society of India, SSPL, New Delhi. The topic on fundamental of semiconductor crystal growth and epitaxy. The way Professor Sharma talked about the fundamental of semiconducting materials, nucleation and crystal growth is commendable. And Professor Sharma explained the phase equilibrium of the material in very well manner, which is interesting and informative for all the participants. So I am sure that a student and the professor will definitely benefited from the information shared by the Professor Sharma. Thanks again, sir. I once again express my heartfelt thanks to our invited speaker of the today's session. We are fortunate enough to be backed by the members of the organizing committee of the process. I am thankful to the delegates and participants for sparing time from these busy schedule to be with us virtually. I thank you all for your attention. Thank you for joining. Thank you very much, sir.
Thank you. Thank you, sir.
Thank you. Bye-bye.
Sharma Saab. Thank you, sir. God bless you, sir. God bless you. Thank you, Zubair. Thank you, Zubair. Thank you.
Sir.
Thank you for taking time. Thank you. Thank you all. Thank you.
Yes,
Naklesh.